today's webinar, it gives me great pleasure to introduce my friend and colleague, Dr. David Grimes. David is a PhD molecular geneticist. He worked in various university departments before moving into the field of pre-implantation genetics and prenatal genetics in 2005 when he joined a company out of Cambridge called Bluenome. Bluenome was instrumental in bringing prenatal diagnostics to the NHS and other areas globally with its microarray technology. And in 2008, launched the first real widely used microarray technology for pre-implantation genetic testing for aneuploidy, PGT-A. That product was called 24Sure. David was instrumental in the growth of that area. And in 2012, Bluenome was sold to Illumina, the next generation sequencing company. David was an associate director of Illumina in the reproductive health group, where he helped in many areas, especially customer support. In 2016, he joined Genesis Genetics in the UK. And in 2016, April 1st, Genesis Genetics was acquired by CooperSurgical, and he moved along to CooperSurgical. David is a director of the global business development area, an expert in PGT-A and various PGT technologies. It would be really interesting to hear his views on the question asked today. Myself, my name is Tony Gordon, PhD. I'm the Vice President of Global Business Development and have been involved with PGT since 2008 as well, and have an interest in all areas of PGT, particularly aneuploidy and cytogenetics. So without any further ado, I'd like to ask David to give us your insights on are your PGTA results giving you the best chance of success for your patients? David.
Thanks for that lovely introduction, Tony, and it's a great pleasure to be able to present this today. So as Tony said, at the end we'll take questions, so please keep your brains thinking, and we'll take any questions we can as we approach the end of this webinar. So the webinar is, as advertised, are you giving the best chance of success to your patients through the utilization of PGTA? So we'll be covering a few topics today, starting off with, are all PGT results the same? This feeds into why accurate results are important and how PGTA-I2 can really help with that. But really, we'll be looking at how your PGTA test can provide maximum information. We all want, at the end of the day, the best for our patients, the best for the clinics. Everybody's looking to drive the best outcome that they can. And then we'll just summarize where we are today with the technology and where PGTA may be going. So just as a very quick recap, although today we are talking primarily regarding PGTA, what we also have is SR. So just to be clear, both PGTA and SR utilize our PGTA 2.0 technology. So they're both copy number counting tests. They both use the same underlying technology. So it's very important to understand that our best-in-class copy number counting and structural change assessment is used in both these testing methods. We won't really be talking about PGT-M today, but just to again recap, we do also do the PGT-A on top of the PGT-M testing, and that would also be utilized in the PGTA-I2 technology. So, as I say, advertised as PGT-A, but it does have implications for all three of the PGT tests that we offer today. So are all PGT results the same? Now, we've got to be careful here, and we don't mean that are they named the same. So are they named euploid, aneuploid, mosaic? Yes, absolutely. But we're talking about the outcome. So really, when we say, are all PGT results the same, what we're really looking at is, do the outcome from what's been reported matter to the patients? Do they matter to the clinics? And the answer is yes, they do. It is very important to think about the technology and the accuracy when it comes to patient management. So this was data that was presented by a leading clinic in the US at ASRM this year, just a few weeks ago. And they had been using the old subjective methods for PGTA calling and through CooperGenomics. And then obviously we launched PGT-A2 in October 2019, and they had accumulated nearly a year's worth of data. As I say, it's a large centre, so a big data set. And what they found through a comparative study and a retrospective study is that there was a relative 13% increase in ongoing pregnancy and live births per embryo transfer compared to the subjective and prior methodologies. So 13% is a massive gain in IVF, absolutely massive. Excuse me. So if we look at it in more detail, then we have to acknowledge it's a single center study, and it is an internal retrospective study comparing clinical outcomes from historic to the today. But as far as anybody can tell, these are the same patient cohort effectively, no changes in demographics. The only thing that really changed was the technology doing the PGTA. And the thing that jumps out is this statistical increase in live birth rate with PGT-AI 2.0. So a massive increase from previously it was 61%, nearly 62%, to over 70% live birth or ongoing pregnancies per embryo transfer. And when we look a bit deeper, we can see the implantation rate is slightly higher with PGT-AI 2, and the clinical pregnancy rates are also really showing this increase. So it's driven not so much by an increase in implantation rates, but actually it's being driven by, if they do get an implantation, the chances of that implantation going on and forming a healthy live birth is very much improved. And we can see that in more detail here. So we can see with the old method, the subjective methods, there's a big drop between implantation rate and clinical pregnancy rate, and another drop again between the clinical pregnancy and ongoing pregnancy rate. So these are your implantation rate is effectively your biochemical pregnancy or positive pregnancy test. And we can see with PGT-AI2 that these drops are much less significant. So we're getting that implantation event. It is a euploid, it's implanting well, but because we're better at delineating the euploids from other embryos, then they seem to, well, they demonstrably do better in outcomes. And by the time they got to ASRM, they had enough data to really look at these early pregnancy losses in much more detail. And it actually became apparent that the difference in the biochemical loss rate was again significant. So with the old subjective methods, getting on for 12% of implantation events failed to then go on and create a sustained pregnancy, and this was reduced to below 5%. So hugely significant for the patients. They're very excited. They've got a positive pregnancy test kit, and now we have a much higher chance that that will go on and form a sustained pregnancy. Again, unfortunately, in both art but also natural conception, even a sustained pregnancy will sometimes be lost, and this is unfortunately just something that occurs for multiple reasons. But this again, whilst not statistically significant, the spontaneous abortion rate is also seen to be reduced. So overall, what we are seeing is this massive increase in live birth rate, driven primarily by those who become pregnant staying pregnant, and that for patient management, all sorts of psychological reasons, that's really great news for the patients and the clinics. And if we didn't think that we could improve PGT-A, there wouldn't have been, over the last 30 or so years, this massive investment and iteration of technology we would have just stuck at the three fish probes. Day 3 does the job, great, wonderful. But this didn't really work. It showed promise, but it wasn't particularly transformative. But people still believed in the technology, and so we saw these iterations. And really, the first 24 chromosome analysis was commercially available in 2008, or ACGH 24 Shore. But we knew we could do better as a community, and this is when we introduced NGS. And then suddenly we saw a step change again in performance between our ACGH and NGS. Some companies have decided to stick here and just say, we've got an NGS solution, that's it, that's good enough. We thought differently, and we thought there was more we could do. And so we launched PGT-A in 2018, which is our version 1, which I'll talk about in a minute. And again, iterated again about a year later for PGT-A 2. And the key point for all of this is we're generating more data, but we're not just generating more data because we can generate more data. We're generating more data because it gives us clinical utility and improved outcomes for patients. So this is really why we at Cooper really believe that we should keep iterating and improving the PGT-A technology and PGT technology generally. But it's not just from our side that we see the changes in technology. This is data from HFEA that was published earlier this year, a retrospective look at data from 2014 to 16 with PGT-A. And, you know, we may think 2014 was quite recent, but in many ways it's quite old data now. And what we really see is that there has been a step change with the amount of live PGT-A, and fresh biopsy, fresh transfer has really more or less disappeared from the market now. And in 2020, it would be down here somewhere because nobody really offers it anymore. But we saw this growth in frozen PGT-A live birth per embryo transferred. And again, we're now thinking about trophectoderm biopsy, not day 3. Pretty much everybody now only does trophectoderm, and from the graphs we've shown now, for some clinics, that this data point in 2020 is actually per embryo transfer, even up to 70%. So there's changes in technology use over time have delivered for the clinics, and we need to keep thinking on that front. But there is also changes that we mustn't forget being undertaken within the actual IVF clinics themselves, with culture changes, vitrification improvements, etc. So we've talked about how changes in technology have improved outcomes, how changes in technology are still continuing, but why are they important that go beyond just the headlines? So really, I think we would all agree that subjective calling in any walk of life is subject to the individual's interpretation, to the mood that they're in, how cautious or not they are as an individual. So it's been shown even with embryology that you show the same image of an embryo and they'll grade it a BB one day, and then they'll come back to it a week later, same image, and grade it a BC or something. They, depending on what has happened during that time, may change their opinion of how good a plot is, what they've seen recently, what they had seen even in the previous hour. So if we were faced with this kind of plot that we can see on the left here, which we used to see a lot, we would be very concerned about chromosome 20. Was that a mid-range mosaic? Should we be reporting that? Or was it just part of the background noise of this particular embryo profile? Now, if we got it wrong, then that could lead to an adverse outcome that was potentially avoidable. If we were to say, call it euploid, and they had a miscarriage and it came back as an aneuploid product of conception, this would be a concern. Equally, if we called it mosaic, and the clinics don't like transferring mosaic, you've denied that patient a transfer. So by using a smart algorithm and AI and using live birth outcomes, we could model this much more accurately than just a theoretical bright green line. to see what deviation we'd seen in over 1,000 live births, and we'd seen enough of this type of noise before to say, hey, this is just part of the assay, it's euploid, and we can report it with euploid very quickly and move on to the next embryo, ensuring that this embryo is correctly reported and enabling a euploid transfer. And what this gave us very quickly is a relative increase in the number of euploids being reported by 7.7%. So this was really good to see, but it came also with a decrease in the aneuploid embryos. So once an embryo, in many clinics, once it's labeled aneuploid, that's it. It's considered not suitable for transfer. So as well as having more euploids, we also had a decrease in aneuploids. But the other hot topic for years has been mosaicism, and we managed to decrease the number of mosaic embryos that we reported as well. So overall, this resulted in some fantastic news for the patients. We had in every age group more euploids available for transfer. But the other great news is that they were distributed across the patient. So it wasn't like a patient who already had one euploid suddenly had 2 euploids. It was some patients who never even had a euploid now have a euploid. So this was really great to get out there and allow an increased number of patients the opportunity to have a euploid embryo transfer. So the other thing that we need to think about is mosaicism. So we need to think that in 2019, after a reasonable number of mosaic embryo transfers had been collected, there were increasing evidence of how to stratify embryos, and this led to the PGT-A positional statement. And top level, you could say that the PGT-A as a screening tool should allow the prioritization of embryo transfer into 3 categories. Your first priority is a euploid. If you don't have any euploids, prioritize a low-level mosaic. If you do not have either of those 2 available, then you would consider transferring a high-level mosaic. Now, there were some secondary priorities, which are clinical decisions. If it's a live birth trisomy, potentially you may consider not transferring it, or a chromosome that may lead to severe intrauterine growth. So not every chromosome is the same potentially, but these are the kind of things that we're looking at. But again, the PGT-S additional statement said very clearly that you should be looking at the 20 to 40% for low level and 40 to 80 for high level mosaicism. That's where they drew their guidelines. That's where we report today. So since that, this is data accumulating very fast, and in early 2020, this data was presented from the first 822 mosaic transfers. There was a great presentation at ASRM this year where they've now collected over 1,000 mosaic transfers. We're waiting to see the final slides from that, but it builds on this work very nicely, where it shows that even a segmental mosaic can have an impact in this data set, not significant at low level, but their latest data suggests that it is. And then a chromosome mosaic will perform worse again than a 2 chromosome. And we see this gradual drop off in performance, but there is a clear definition that they've scored it below 50 and above 50. It was a multi-center data collection. This is overall where they scored their data. But again, there is this clear difference between a low-level mosaic and a high-level mosaic in performance. So in terms of managing patient expectations, managing patient care, it's very important to know where this embryo fits in terms of outcome, because that will change the patient conversation. It will change the way that you manage expectations and potentially how that patient is consented for that transfer. Having said that, of course, it's worth remembering that even these complex mosaics had some chance of success. and therefore should not necessarily be discarded just because they're complex mosaic. And this is why we believe it's very important to not score these as aneuploid, because that would be denying those patients their potential last embryo transfer that could result in a live birth. So PGT-A technology was, I'm not going to go through this in too much detail, many people have heard it before, but it was built on the biopsy data from 1,000 embryos which we'd got, which resulted in live births. And so we knew that anything we see in that profile was insufficiently deleterious to stop that pregnancy from having a live birth. So every embryo we score is these days scored against embryos that we knew went on to perform a healthy live birth. This is our truth. And this is where AI needs to be. You need known outcomes, known truth to inform your future decisions. And so we then validated it from over 10,000 embryos. And when I say validated, it doesn't mean to say that it got the same result as it did with our subjective methods. Far from it. It just means that we understood how the algorithm worked and we believed that that was the correct answer. So this provided us with a statistically robust and accurate interpretation that removed all subjectivity of calling. After we'd launched that, we continued to generate feedback from the field, and also sequencing technologies improving every year. And so we were able to utilize, being a global company with a large volume of samples coming through, an increased performance sequencer, so a much bigger sequencing box. And this allows us to produce over 10 times more data per embryo. That data not only allows more accurate sequencing through paired-end sequencing, but it gives us a new way of analyzing the data, which is SNPs, single nucleotide polymorphisms. And via NGS, this was a world first for PGTA through global NGS. The key point is we now have two methods for scoring aneuploidy. And I think most people would agree it's better to score something twice where you can than rely on a single metric. So this was really powerful technology. Again, this is quite a technical slide, and we have a whole presentation on YouTube on how PGT-AI2 works in a white paper, but very quickly, you can assess the unique patterns of inheritance from mum and dad into the embryos and look at what's called the SNP ratio. So you would have, if it's a monosomy, you would only have one. If it's heterozygous, it'd be 1-to-1. And we can look at all possible dosages and parental inheritance patterns. So this can be for a region of interest in ROI. So this is particularly important for PGT-SR, where we're looking for a known structural aberration. We can look at it at a chromosome by chromosome level, or even just take a more global approach and look across the entire genome. And again, just to try and put a few diagrams to this, we have a clinical resolution of 20%, and that is absolutely worth mentioning. We recommend that you biopsy 5 to 7 cells. So if you've got 5 cells in the tube, each abnormal cell is 20% of your total. So this makes mathematical and biological sense. Even in an ideal world with the following wins, you could potentially theoretically see 10%. In the real world, from a clinical perspective, this doesn't make sense. So we have a clinical resolution of 20%. And what we see is if it was a homozygous, you'd have AA. So this is, you've got only inheritance from one type of the variable. If you had BB, you have the other form of inheritance. But if you're for some SNPs, they're called that they inherit in a certain pattern, and you would get a version from mum and a version from dad. And this has been known for inheritance. So if we think of blue eyes, brown eyes, we know that brown eyes are dominant, but you can be brown-eyed with the allele for the blue eye. 2 brown-eyed people come together, they can have a blue-eyed child. So for certain SNPs, you are heterozygous. You carry both forms of that SNP, and that would give you an AB or heterozygous. And we can look across the genome and look at these. If you then find you have an over or underrepresentation of one version, then you know that you have a mosaic cell, where a mosaic collection of cells where some cells have overrepresentation of either mum or dad, and this is what gives us a mosaic calling. And ultimately this transfers into, these are clearly aneuploid, these are clearly euploid, these are the low-level mosaics, and these are the high-level mosaics. And this just ends up as being a primary assessment, that we have the primary of this classic copy number variation, the CMV. We have the secondary of the SNPs, and that means that we can reject noise and reduce artifacts. This is particularly important to ensure that what we say is euploid is euploid. We don't want to be calling a noisy chromosome mosaic if it's just artifactual noise. Again, technical accuracy, very important for PGT-SR, allows us to go down to 5 megabase calling. So if your SR case is telomeric, this is very important. And as I've just stated, best in class mosaic calling. So this gives us our reporting categories that we use at Cooper. So as I say, these follow the PGT-IS guidelines. 20% or below is euploid, 20 to 40 low-level mosaic, high-level mosaic 40 to 80, greater than 80% mosaic is aneuploid. It is worth noting that embryos can have multiple abnormalities, and it's the highest level that determines the status of that embryo. So if it had a high-level mosaic chromosome 3 and a low-level chromosome 1, ultimately this would be scored as a high-level mosaic. Equally, if there's a single aneuploid chromosome in that embryo, that whole embryo is scored as aneuploid, no matter what other chromosomes may be showing. So we're trying to maximize the information that we provide to clinics. Without going too deep, we're not trying to get into identifying novel diseases or de novo changes in the embryos, but we are trying to give the most information we can to the clinics, and therefore improving the chances of success for the patient. And if that success could be measured in multiple ways, one of which that success may be just a better understanding of what is driving their infertility. So really, by utilizing this new technology, we can really look at how we can maximize the information coming back to the clinic and to the patient. So PGT-A is an aneuploidy screen. We're looking for aneuploidy in the embryos and basing transfer decisions based on that report of aneuploidy. On top of that, there is assumptions made as to where aneuploidy is derived from. So we tend to think of aneuploidy primarily as a maternally derived condition and event, and it's been estimated that at 90% of the time that is correct, but there's still these 10% of patients in aneuploidy which is definitely paternally derived. Again, there is the assumption that a segmental change is most often of paternal origin, but there's still 30% of segmental origin is maternal. So rather than just using that broad brush approach and making decisions, then we can look at the parent of origin of that aneuploidy to provide that direct assessment. So we'll take an example of a patient couple. Maybe the female is 35, for example. We would expect 50% of their embryos to be euploid, 50% to be aneuploid. Now, if they get a PGT-A result and everything is aneuploid, the first thing that you may think is premature oocyte aging or some form of maternal issue, which goes beyond the expected, but that's as far as you could take it. These days, with our technology, you can now have a retrospective test and find out if that is truly the case, or whether there is also a significant sperm issue, And by having that, you can have more confident conversations with the patient. You know where the aneuploidy is coming from. It would either provide patient peace of mind, they have that understanding, or if you are going to move on to donors, it's done in an informed way and not on an assumption. And we think that that is very important and not to be underestimated for some patients. We also have the ploidy detection. So ploidy is the number of genomes that you have. You should have 2 genomes, one from mum, one from dad. That's 2PN. But it is estimated that 1 to 3% of IVF embryos result in mode of pregnancies and miscarriage, and that in a large number of cases because they're either 1PN or 3PN. We also know from up to 15% of first trimester miscarriages, which come back with a confirmed aneuploidy, have also resulted from these unusual fertilizations, the 3PNs. Now, this can happen in both IVF and natural conception. It's not an IVF phenomenon. But haploidy is where you only have the maternal component. So the egg just hasn't been fertilized, but it's still gone through cell divisions, it's gone on to form a blastocyst. These can also sometimes implant. But we can now molecularly check this. So by having the cheek swabs from mum and dad and DNA from mum and dad, we can then confirm if these embryos are haploid, triploid, or of course, just 2PN. So it's a molecular check for the 2PN status of the embryos. And this is important because it was estimated by a paper in 2018 looking at PGT-M embryos that up to 75% of previously scored 0PNs were actually 2PN. And again, near getting on for 50% of 1PN blastocysts are actually diploid biparental. The fertilization event has been not correctly scored or has been missed. So if you were to then discard these embryos, you're discarding viable embryos for transfer, which is particularly important in patients who have a low number of embryos and every embryo counts. So PGT-A through Cooper Genomics has 2 forms of test. We have our standard test, which anytime you order PGT-A through Cooper, you get our world-leading PGTA-I2. It's just our standard test, which offers the best-in-class aneuploidy detection of down to 5 megabases, mosaic detection of anything above 20%. And for the basic test, we can do all forms of male triploidy. So XXY, XYY, they're all detected. With our PGT-A plus, which is an additional add-on to the test, which, as I say, can be done both retrospectively and prospectively, depending on clinical need. It does require parental cheek brush kits, so DNA from mum and dad. But on top of our core test, which you get with everything you order from us, you also get this origin of meiotic aneuploidy, all forms of triploid and haploid, but of course this molecular test of the embryos. And this is important for some patients and increasingly seen as an added test that can help patients get a transfer. So we have these 2 tests, our core test, which has the more data and the 2 independent tests, and then our plus test with these additional options. And please look at our YouTube channel to find out more on how this testing works. But I like to think about it like this, and this is really where I see one of the key benefits of PGTA-I2, but also thinking about when you're offering PGTA test to the patient, you're opening doors to knowledge. So if we think of PGTA-I2, our standard test, which is what you get out the bat, I'm just highlighting here, even though it's PGTA and just straight PGTA, we still generate all the SNP information, this unique inheritance pattern information. So these SNPs exist and they help us do the key part of the test. However, this information is of course available so that were parental samples to be either run at the same time or retrospectively, you still keep this, but you've opened the door to this additional testing for the patients, which allows further discussions dependent on the results. Were this test not run in the first place, then you lose the option of adding this at a later date. So it's worth thinking ahead, you know, what can we offer our patients in the future if this result comes back in a strange way? Well, the good news is we can always go and do some extra exploring if we need to. So even though it is an additional test, it is there available if you've had PGT-A run 2 in the first place. The other aspect that I really wanted to cover is classification rate. So as I said right at the beginning, we're not talking about revolutionizing PGT-A in the language we use in reporting. We're not saying that we would report using a whole different subset of language. What we're talking about here is if you say it's euploid, is it euploid? Is it aneuploid? Is it aneuploid? And the good news is the majority of ours, the overriding category that we have across all age ranges is euploid, 44%. And this is important because we're not being so stringent in our embryos trying to call them euploid that we're basically saying only a small percentage of embryos you send to us are euploid. We've maintained this euploid level at 44%, even though we're doing more stringent classification. We are, more stringent analysis. It's actually pushed down the number of aneuploids. Again, we do have these low-level mosaics, which many clinics will consider transferring. So a very important 7%. These high-level mosaics, there is a bit more uncertainty as to whether or not to transfer them, but they are at least available if the patient and the clinic agree, so that's worthwhile. So you add all these together and you've got 58% of embryos that we test are potentially available for transfer. The other quality that we need to think about is the no results rate. So unfortunately, with any test, whenever you submit a test, we always get some that fail. And with our iteration of the technology, we've actually driven down our failure rate. So unfortunately, we still get about 1% just under of samples where we can't do a whole genome amplification at all. That stage fails. But we have now reduced our quality failures, so those where we've generated an NGS profile, but we can't interpret the result, or in this case, the algorithm can't interpret the result, is now down at 2% of all samples received. So we're now at a failure rate of, overall, it's about 2.8 to 2.9% of embryos fail to get a result. This is down significantly from where we were previously and other providers' ability to provide results. So we're very pleased with not only are we getting better data, we're also getting a higher pass rate these days. So that's great to see. Here are just some, this is a bit more general interest. One thing that we note as a global company is we test the sex chromosomes for most embryos that come into the door. We look for sex chromosome aneuploidies. For those where we can identify the sex, by chance, we're getting slightly more males than females. About 2% more embryos are male than female. Why that is, I leave up to others, but it's just an observation that we see. As I say, there are some embryos which, due to the testing required, we can't confirm the sex of those embryos. But about 4% of all the embryos that we test show some form of polyploidy. So that is where they've got either 1 or 3 copies of a genome rather than the expected 2. And of these, a lot of them are actually female triploid, XXX embryos. So if we look at it in slightly more detail, we can see that these all with a Y would be called male triploidy. So you add all those together and what you're left with is female. So it's it's not quite 50-50, but we can see that there is a lot of previously undetected female triploid embryos coming through. So in summary, I would just like to wrap up and just say that for sure, PGT technology improvements can significantly improve IVF outcomes. We've seen that over the last, well, since I've been in the industry, so 12, 15 years now. As we've got better understanding, well, as advancing the technology has increased and we can get more sequencing data, we can give more complete understanding of the genomic content of embryos. And that ultimately should lead to better choices and outcomes for patients. And we've certainly seen it in live birth rates. We have started to see a lot of clinics now send us embryos for PN checking so that they can make informed transfer decisions based on content rather than a questionable fertilization event. So we're definitely there offering better choices and better outcomes for patients. And so with that, I would like to thank you for your time, and I would like to very much open this up through the Q&A box for any questions which anyone from the audience would like to submit. So thank you.
Thanks, David. Really great presentation. And we do have some time for some questions, and we have had some questions come through. But if you have any other questions that have come up as you've gone through the webinar, please feel free to put them in the chat box as well, and we'll try and get through to them, or we'll contact you later. So the first question that's come up, and it's a really interesting one, I think, because it kind of takes from what you're talking to the technology to the outcomes, and it's are UK clinics implanting mosaics, and what are the outcomes of those? And maybe just comment on outcomes of mosaicism generally.
So I think there is an increased acceptance to transfer at least low-level mosaics in the clinics. There is some data now that clearly shows they have the potential to form a healthy live birth. Now, obviously, the numbers are relatively speaking still small, and people will rightly prioritize a transfer. It's, I think, everybody in the community, but certainly our community, to get more outcome data from these transfers, build up the picture. But from what we've seen, there is an increased acceptance of transferring low-level mosaics under proper counselling and consent, and very occasionally perhaps a high-level mosaic.
Thanks, David. I mean, it's a really interesting point in general, transferring mosaics, and you know, where do you think the guidance is going to go? You know, when we get more mosaicism data.
Yeah, well, the discussion at ASRM, which I thought was, and they're actually building up an online tool which could be very useful for clinics, is you will end up with a sliding scale. Perhaps, I know we don't like to overcomplicate things, but I think with the data that we're now getting, it's very clear that a low-level segmental embryo is going to be less deleterious to outcome to a whole chromosome mosaic, and a low-level whole chromosome is less detrimental than a high-level whole chromosome. So I think we will end up with some stratification of transfers, but I suspect and hope for, at some level at least, that the reporting will remain fairly consistent with where it is today, with low-level, high-level, aneuploid and euploid in 4 categories, with then a subset of advice for clinics on how to stratify their transfers. Otherwise, it starts to get incredibly complicated for patients and clinics.
Well, it is incredibly complicated. I agree with that, and I think that's why genetic counselling is really good in this situation, if required. And you know, I think you have to think about things like live birth trisomies as well. Would you want to transfer those? And I think the guidelines are still being refined. So it's pretty interesting.
I agree. I mean, Tony, talking, there's another question that comes in talking about triploidy, in fact, and PN checking. I mean, I've talked a lot about it here, and I mentioned it in passing, but do you see much IVF clinics using PGT-A2+ for PN checking, and what's your thoughts on that as a technology?
Yeah, well, it's interesting, you know, how much polyploidy we're picking up, because every one of those embryos that we pick up as a polyploid, and we pick up, you know, 4% here, will have had a FERT check and would have gone through as a 2PN. And then when we've tested them, they appear not to be 2PN. So I think it just says how difficult PN checking is. You know, physically, the PNs can be stacked, so you might see the incorrect number. You might see 2 instead of 3. And PNs can fade and have different timings. Even if you're using morphokinetic incubators, it's still hard. And then if you're seeing 4% of embryos wrongly classified as diploid in our analysis, you get the flip side in that how accurate are the ones that are called 0PN, 1PN, and 3PN by FERT-check. And that's something that we're beginning to see as well, whereby labs that are doing FERT-check, and you know it is a difficult thing to do, are doing FERT-check and calling embryos 1PN, 0PN, 3PN, sending us those for PGT-I 2.0 plus, and they're coming back as euploid. And there's some literature around that. And I think it's really important to consider giving the best chance for the patients. You know, if you don't have anything to transfer, you know, have you cultured those embryos? Do they make blastocysts? Do you want to biopsy them, try them? And, you know, already we've had some nice examples from UK clinics where they've done that for embryos that are being classified as failed FERT-check and come back as euploid, and I think being implanted as well. So, you know, I think it's trying to get, I think you summed it up quite nicely. It's trying to get the most complete genetic picture of the embryo from the data. And I think that's one of the things we're able to do. You know, we're able to get so much more information. I mean, the core test is brilliant because it has the copy number analysis and SNPs and reduces the noise, gives us less fails, gives us less mosaics, gives us more euploids and mosaics to consider for transfer. So it's really good. But then I think it's going to be interesting to see how people take on the 2.0 plus, because it can give you so much more. And I think we're only just beginning to understand how much more it's going to be able to give options for clinics and patients, embryologists, clinicians.
Yeah, wow. I mean, there is a lot of stuff there for sure, and I'm sure there's more to come from the technology as we move forward.
We have a question come through for you, David, and it's one that is quite a key part to the technology and PGT-A 2.0. Why have we gone to the trouble of using validation with live birth rates when we could do it and have done it so easily in the past with cell lines?
There's many keys to that question, and I think it's absolutely worth addressing. And so, of course, indeed, when I started way back when, now, you know, you couldn't get embryo biopsies with known outcomes in the same way. So cell lines you could buy, you can get cells from commercial companies which have known cytogenetic outcomes. They're immortalized cell lines, but they're not actually, over the years, they can change. And also a cell cultured cell grown in media is a human cell is very different from an embryo cell. I mean, the size of a trophectoderm cell is much larger. The way that they are developing is very different, and so you really want to be comparing like with like. So by the time you've taken a biopsy of those cells, taken them through an NGS run, you have fundamentally changed a process compared to picking a few cells out of liquid culture and hoping that that is representative of a biopsy. So just by doing that, you've got a better representation of the truth. Then because we've tracked it all the way to live birth outcomes, we know the endpoint is live birth. I mean, that embryo has been a great embryo. It's implanted, it's gone on, it's a live birth. So anything that we then see in a profile from that embryo has to be essentially noise generated by the technology. So when I say the technology, that's everything involved in taking a biopsy through to sequencing. And by the time you've got 1,000 of them, then you've got a really strong baseline for understanding the kind of artifacts that you would see in a euploid embryo, which then goes on to form a live birth, which you would just never get from a cell line. You have no outcome from a cell line. experiment. All you have is an assumption that the cell line was something, and it looks like that on the plot. There's no final endpoint, and that's where we're really strong. We're basing everything against a final endpoint of a live birth.
Cool. Thanks very much, David. Great answer.
Oh, here's one. So you've just talked a lot about how you know you're accurate, but how do we know it's accurate? I mean, what is the accuracy of PGT-AI2, Tony?
So the accuracy of PGT-AI you can do in a number of ways. Basically, you look at outcomes. So the easiest outcome to judge is by looking at euploids that have been transferred and seeing what the outcomes are. And what I mean by seeing the outcomes, we don't clearly sequence babies that have been born, but what I mean is if there's been a miscarriage and material is available, we look to see whether that was euploid as well, to see whether we've missed something in the analysis. And it is possible, if an embryo is mosaic, that you could have taken a part of the embryo that was euploid and missed that other cell line that is aneuploid. So do we miss mosaics? Well, I can tell you that we've had one mosaic in 7 years that has been reported at POC so far. And there's a very nice paper from Friedenthal, NYU, where they looked at both PGT-AI and the previous subjective technologies and saw less than 1% of embryos that have been transferred as euploid that had an outcome with a mosaic result. So it's a very robust technology from that way. And that's a good way to think about it. The thing that's harder to do is to transfer aneuploids. And obviously, transferring a known aneuploid is a very difficult question. I mean, I don't think anybody's really going to do it in the UK. The way that people have got around that is by doing what they call non-selection studies. So they biopsy embryos, and then they don't tell the patient and the clinician the results, and then they're blindly transferred, and then you look at the outcomes. And there was a nice publication from Teagues et al. Just this year where they did 100 transfers. So they transferred embryos and looked at those aneuploids. Now, those aneuploids, as you might expect, didn't create a live birth. The problem I have with this technology is they also created 30 late miscarriages that could have been avoided. So it's ethically challenging, and it's a test that we haven't done with PGT-AI 2.0. So yes, we can't confirm if we call something aneuploid that it wouldn't produce a live birth, but we are transferring mosaics, and we do see that mosaics have a lower live birth rate than euploid. I mean, I think it comes down to your ethics, and I think that we're fairly comfortable with that when we say something's aneuploid, it is extremely unlikely to result in a live birth, but we're not going to put women through the terrible unnecessary miscarriage to prove that as a scientific experiment. Thanks, David.
That's a great answer. Thanks, Tony. So I think we're pretty much on time. Actually.
Well, no, I think we have. I think we have time for a couple. We won't let you off the hook yet, David.
Okay.
Other companies have AI technologies. What's the difference between the Cooper Fertility Genomics Solutions technology?
So obviously, I can speak more on the Cooper than others. We've got more insight on that. But what I would say is fundamentally, as far as we're aware, at least, we are the only company using AI that goes all the way through to live birth and tracking the robustness of that over multiple thousands of post iteration runs. So our AI algorithm is very, very much based on truth, and we continue to check it and iterate it, and hence PGT-AI2, and it's based extensively on real big data and absolute truth. So the other AI that I have seen is being based more on running thought experiments, running mosaicism, dilution experiments, and just saying, yeah, well, we made a 20% mosaic mixture. That's what it gave us. We'll call that AI because we've seen it in some test runs. There's no truth at the end of it. We have also used known segmental cases from translocation cases to prove accuracy in robustness in calling segmentals across all chromosomes, across all possibilities. We've used other technologies to validate our calls, such as snip-based technologies to validate all of our calls, and really fed that into a massive data set and known outcomes. So everything that we're seeing is based exclusively on embryo data and live birth data, and not on anything to do with cell lines or thought experiments.
Great. Thanks very much, David. Well, as you say, we snuck that last question in, but we're running up to the end of the presentation. So we'd just like to wrap it up now. I'd like to thank David for his great presentation. I'd like to thank everybody for attending. And we have a number of webinars upcoming. We will be in touch to let you know when they are. We have one next Wednesday, where we're looking at a panel discussion with some of the clinicians and embryologists in the UK. We're really looking forward to people joining that one, and other webinars will be advertised. So for now, I'd like to say thank you for attending, and we look forward to you coming to along our next webinars in the series. Thank you.